Okay, I can. So let us continue with good numerical problems. I can give you one more illustration. A positive charge Q is uniformly distributed throughout the volume of a dielectric sphere of radius r. A point mass having charge plus Q and mass M is fired towards the center of the sphere with velocity v from a point at a distance r and which is greater than r from center of a sphere, from center of a sphere. Find the minimum velocity v so that it can penetrate r by 2 distance of a sphere. This is your question. Okay, let us solve this. क्वेश्चन क्या है कि एक डायलैक्ट्रिक है जिसका रेडियस r है और q चार्ज इसमें डिस्ट्रीब्यूटेड है और सेंटर से जो डिस्टेंस है r, यहां से हम प्लस q चार्ज और भी निकालना है कितना हम भी मिनिमम दें ताकि ये यहां पे आ सके। ये जो रेडियस है यहां से यहां दूरी r by 2, मतलब with how much velocity you need to project this charge having mass m so that it can penetrate and reach at a radius r by 2. Why are you doing work? आप वर्क क्यों कर रहे हैं? बिकॉज आप इसके इलेक्ट्रिक फील्ड के अगेंस्ट आपको वर्डन करना होगा। यदि इस चार्ज को आप मोशन देते हैं इस इलेक्ट्रिक फील्ड के अगेंस्ट तो क्या होगा? इसका पोटेंशियल एनर्जी चेंज होगा। जब भी हम किसी फील्ड में चार्ज को मोशन करते हैं तो उसका पोटेंशियल एनर्जी चेंज होता है। और ये जो आपका इलेक्ट्रिक फील्ड है ये इलेक्ट्रोस्टैटिक इलेक्ट्रिक फील्ड है जो कंजर्वेटिव होता है नेचर से। तो हम लोग ये जो डील करते हैं इलेक्ट्रोस्टैटिक फील्ड में चार्ज को, मोशन को, और बेसिक जो फार्मूला है, बेसिक टूल्स है जो हम हमेशा यूज करते हैं, यही यूज करते हैं. दिस इज कैरेक्टरिस्टिक्स ऑफ कंजर्वेटिव फील्ड. चेंज इन एनर्जी, पोटेंशियल एनर्जी, चेंज इन काइनेटिक एनर्जी इज गोइंग टू बी 0. तो आप कंसिडर कर सकते हैं यहाँ पे भी है, यहाँ पे आके पेनिट्रेट करें तो यहाँ पे 0 वेलोसिटी हो गया है. तो चेंज इन काइनेटिक एनर्जी इज हाफ mv². And Q V final minus V initial. Changing potential energy is this one. Okay, अब V find करना है, then Q. So V final क्या होगा? ये जो यहाँ पे है पोटेंशियल क्या होगा? और हम लोग इक्वेशन जानते हैं किसी भी स्फेरिकल चार्ज डिस्ट्रीब्यूशन के अंदर पोटेंशियल क्या होता है? Vf. हम लोग पढ़ चुके हैं V सरफेस by 2 3 minus r² by r², और V surface that is Q by 4 pi epsilon naught r, and 2 से जो मल्टीप्लाई होगा तो 8 हो जाएगा. 3 माइनस r की जगह पर हम पुट कर सकते हैं r by 2 का होल स्क्वायर बाय r². And it is going to be 4 12 minus, then it's going to be 11 Q and 32 pi epsilon naught r, क्योंकि r² कैंसिल हो जाएगा आपका. This your potential at this point Vf. Now what about V initial? V initial के लिए ये पॉइंट चार्ज की तरह बिहेव करेगा, और इस पॉइंट पे इसका पोटेंशियल कितना होगा? जो पॉइंट चार्ज का फॉर्मूला होता है उसको हम लिख सकते हैं. दिस इज एक्सप्रेशन ऑफ पोटेंशियल ऑफ पॉइंट चार्ज, बिकॉज आउटसाइड दिस charge distribution, if you want to find the potential, you can just simply write this expression for exactly the same as we have written for point charges. Now just subtract this. Now you can write half mv² Q 11 Q 32 pi epsilon naught r minus Q 4 pi epsilon naught r. You can find the velocity from this expression. Okay, I should write the answer because I want to skip some step, because it's now easy to evaluate the V. So I can write Q 2 pi epsilon naught m, and r will be common 11 to the power 8 minus r to the power r root. This is your velocity. Half is going to cancel out, then 16 and 2 have create common 2 common लेने के बाद ये 8 हो जाएगा, और ये तो कैंसिल था, 2 ही रह जाएगा. 2 pi epsilon naught m r, ये आपका वैल्यू आ गया वेलोसिटी का. तो बेसिकली ये प्रॉब्लम्स में हम देख रहे हैं, बस इसे ही आप यूज करना है. बस एक बेसिक को समझना है कि जब भी इलेक्ट्रोस्टैटिक फील्ड में चार्ज का मोशन होगा, आप you can use these basic equations, only this equation you can find everything. Okay, so we have evaluated potential, how to find the potential of point charges, and also within the charge distribution of this sphere. So I am just going to find out potential of a ring, and and also some given charges continuous for body of continuous charge distribution like ring and disk and some arbitrary shape. So now I will discuss about ring of charge, say Q. Suppose I have a ring like this and it has a given charge Q and radius is R, and this is the point along this axis. This is axis, and you have to find, this is point P, find potential at point P. This is your question. Okay, so I can start with the elementary method. Consider a small section. Okay, like this, and it now can sustain angle d theta. So it has dq is lambda into r d theta, where r is radius of the ring. Okay, so I'm interested to find the potential at this point P. So just define something, charge distribution function, and this is a small elementary charge over there, dq, and it's placed in angle theta. And this is theta and this is theta, a small theta, and this is a small d theta transversed, and this is a linear length r d theta, and you know lambda is charge per unit length, charge per unit length. Now due to this, just at this point, and this say this is y and this is r, you can say this is x, this is r, and this length will be nothing but, you know, x square plus r square. Now potential dV, due to this charge dq, you have dq by 4 pi epsilon naught this distance, x square plus r square. So you can write dq as lambda r d theta. Sorry, here you can have to write it capital letter, because I have introduced a capital letter for radius. You can integrate with suitable integrand. Okay, now you see everything is constant, x is constant, r is constant, only variable is theta. So you can get potential lambda r 4 pi epsilon naught under root square plus r square theta, and it is 0 to 2 pi. The 2 pi angle, it will transverse to cover the entire length. Over entire length charge is distributed. Okay, so over the circle charge is distributed, and total charge is q, and the charge is distributed uniformly. Okay, and I can write q is uniformly distributed. Uniformly distributed. You get something, I think you get lambda r into 2 pi 4 pi epsilon naught under root x square plus r square, and lambda r 2 pi. What will you write? Integrate it, you can get q is equal to lambda r into 2 pi. So this is the total charge. Now you have total charge, potential at P. Now you have found this answer, you have evaluated. So we have evaluated this expression for potential of ring on this axis point at distance x from the center. This is the center of the ring, and this is the point P, and this is your expression. So this is your expression for the potential of ring charge of a ring which has a charge. So what will, when you say x is equal to 0, I mean at the center of ring, how much potential you get? You will get q by 4 pi epsilon naught r, because x is equal to 0, this one, and this is the maximum potential at this point. When electric field is 0, of course, when electric field is 0, you will get maximum potential, because both are, because when you find the maximum one thing, you will get minimum other thing. I mean to say in terms of potential or electric field, when electric field is 0, and potential you are getting maximum. So this is the potential at the center of the ring, and it is maximum, and it goes on decreases as you progress distance in this direction. You advance distance along this direction. If you go from O to P, potential will decreases. At infinity, just put infinity, you will get 0. So V infinity, you will get 0. And also you can go downward. So you can space with x at the center, you will get the maximum, and thereafter it goes on decreasing 0 to infinity, like this, and this is your maximum value at the center. So if you plot this visual graph, now question. Now I would like to do some questions, some illustrations, numerical illustrations. Suppose that we have this configuration, a ring. This is a circular ring. Okay, so I would like to give you some numerical problems to enlighten about all these facts of this, certain things about potential of the ring. You are going to understand now very clearly with these numerical problems. A circular ring of radius r with uniform charge density lambda, that is uniform charge density. Okay, this has uniform charge density lambda, and r is the radius. Of course, it should have radius. So r is the radius, and plus q charge having mass m. Is projected from the point P, and this distance is r, and this distance is r, and coordinate of the point P is r root 3x, y coordinate 0, z coordinate 0. So you project this point charge q with velocity v. Okay. Now find the smallest value of a speed v so that it does not return to point P. This is your question, okay? With what minimum velocity you like to project this point charge having mass m and charge q, so that it doesn't return back. It means it must at least it have to reach this point. Okay. Thereafter, it can go through directly because electric field, it produces along this direction and plus Q charge is projected. So there is a force Fe along this direction and plus Q faces repulsion due to this electric field, because electric field points in this direction and it is transversing in a opposite direction. So it will opposite force cause of the acceleration. Then it must have enough energy, kinetic energy, so that it can surpass this obstruction. This electric field is obstruction for this motion. So it should have enough energy to combat this obstruction, and at least it should reach at this point O. Okay. So because electric field is 0 at this point. If it crosses this point, then it must cross this ring. Then at this direction, electric field is in this direction, E, and plus Q motion. Now force and charge are in the same direction. So from this point O, it will fit acceleration. So it will accelerate after reaching point O. So this is the critical point. If it is able to reach this point O, then it can easily pass, because after that there is acceleration force. The electric field and motion is in the same direction. Okay, so acceleration will be along this direction. So it will support the motion. And here, so how will you find this? Use the conservation of energy again. And what is the potential at the point P? We have found that Q, how can I write the Q? By 4 pi epsilon naught R. Q is nothing but lambda 2 pi R by 4 pi epsilon naught under root, and this R is R square plus root 3 R ka whole square. This is your potential at point P. Now potential at O, you can write simply lambda 2 pi R 4 pi epsilon naught R. What will you get? Lambda by pi by 2 epsilon naught. And what will you get here? 2. You will get lambda by 4 epsilon naught. So you have found the potential at 2 points. So you can find the energy. Now you can use your basic tool to determine the velocity. Okay, very useful. This tool is very useful, because you are dealing conservative field. And if you use this, everything you can get it. Now you will be available to the answer very soon. Now you can write half mv square, changing kinetic energy is to changing potential energy. It has Q lambda by 2 epsilon naught and lambda by 4 epsilon naught. You can find the now V minimum. Lambda Q, this is M half, is going to cancel out 2 epsilon naught and under root. This is your minimum velocity, required minimum velocity. Okay. So I would like to add one numerical problem, more numerical problems, so that I will make you able to understand how to evaluate potential of a ring in different configurations. Now you have two rings and it has a charge Qn and it has radius R. X. Okay, so this is R1 and this is R2 and this is the X. Now we have R1 is equal to 0.05 and R2 is equal to 0.09 meter, and charge is 10 to the power minus 6 coulomb H, uniformly distributed, and X is 0.12 meter. Find the potential difference between the center of the loop. Find the potential difference between the center of the loop. Okay, so you can write V1 and V2. Have to find potential at this point. Then you need to find potential at this point, just subtract it. So this is your question. Find the potential difference between the centers of the loop. This is your question. Okay, if I would like to hint only, because you can find the V due to this charge Q1, you will get Q by 4 pi epsilon naught R1, and due to this ring will produce potential here Q2, but charges are equal. Okay, be comfort with all these things, Q1 and Q2, 4 pi epsilon naught R2. Again V2, that is Q2 by 4 pi epsilon naught R2, due to this charge ring at the center, and again now due to this ring potential at this point, you have Q1 by 4 pi epsilon naught R1. Okay, due to this ring potential at this point, because this point is on the axial line of this ring, so you have evaluated the potential on the axis point on the any point on the axis for this one. So you can now subtract this. This will be your answer. Well, now we have understood about the ring. Now try disc. Now charged disk. This is another continuous distribution of the charge. Continuous distributions of charge. A charge is uniformly distributed over a disk, and this is a disk, and charge is over distributed this surface. Now you take a point on the axial line X, and you say R is the radius of the disk. Check dimension first. At this point, you are interested to find the potential at this point at a height x, at a distance x from the center. Now define how charge distributed at sigma. This is surface charge distribution, because we have taken surface this time. Surface charge distribution. This is a function. We should describe how the charge is distributed, and of course uniformly. This is uniformly. Now I want to evaluate the potential at this point P due to this disk. So I see this disk, many combination of many concentric circle. Okay, just take this elementary ring, this much your thickness. So this charge is distributed this much charge. So what will you write? What amount of charge distributed on this ring? This is a ring. We have taken a ring, elementary ring. We have just here consider, because if you add so many rings, you can make a disk. Arrange rings slowly, increasing from it. Just put so many rings together, you can make a disk. Okay, so I have considered this unit area, elementary area, and having, this is of course ring. Now it is a ring now, and having charge dq. But you need to find dq. You can write dq is nothing but charge, surface charge is the sigma, and this area 2 pi r dr. Suppose this radius is r. Now I want to, okay, and due to ring, this distance, say s. Now s is nothing but x square plus r square. Now potential dV is nothing but dq by 4 pi epsilon naught s. Now we have sigma 2 pi r dr 4 pi epsilon naught. Now put the value of s under root x square plus r square. This is dV. Now you perform integration, you will find d. So now you have sigma 2 epsilon naught. So this, you take a small charge, radius is say 0, and it can expand from 0 to r. Okay, now you can cover the entire surface. If you start integration from 0, r बराबर 0 to r बराबर r, r बराबर 0 to r बराबर r, you can cover the entire disk. Now just evaluate this integration. Soon you will be available to your desired answer. Okay. So should I derive this? Okay, then you can consider x square plus r square is equal to t square. Now have 2r dr is equal to 2t dt. So you can write this, r is dt dt, and this is t, and this is going to cancel out. So integration, you have dt is equal to t, and t is nothing but x square plus r square. So very simple. Left with x square plus r square from 0 to r. So now you have r square plus r square root minus x is equal to 0, you have now, sorry, r is equal to 0, you have x. Sorry, this is x square, and you take this modulus because this point may be also downward. Okay, so I have introduced modulus, so you can go downward too. So incorporating this modulus, I can absorb the negative values too, because you can go downward. You can go downward this point, you can also find this potential. Well, this is your expression for the potential of a disk. Okay, then consider a very large disk. What you will get? You will get infinity, very large. You cannot define actually. This means you can undefined. You have undefined potential. You can't define this, but you can get a potential difference between the 2 points of having a large disk. Okay. So okay, now you can find this one. So well, I'm very much comfortable with this expression, so I can go ahead. So I don't need to trick something here, but little modifications without losing generalities, I can do something, but it's left up to you, because in coming problems we can do something. Okay, now okay, so we have evaluated the potential due to ring and disk and the point charges. Okay, when question will come, you can do the same thing by integration process. Now, I would like to find how much energy a charge distribution has. Suppose we have a charge distribution here. We have a given charge distribution, then it must have energy. It has a self energy, not due to interaction. It has a self energy because. So I just want to find this self energy of a given continuous distribution of charge. Then you have to find the self energy. Starts with the. I mean to say, what is the self energy? You just assemble these charges. Okay, just put a small dq charge here, then another small charge again, then doing in so many ways, you just assemble this amount of charge. Okay, so when you put this small charge dq, you have to work against this already charge placed there, because we don't allow here to put this a small charge, because it will repel. So energy required to assemble the charge, say a total charge Q, I need to bring this charge from say infinity, okay, because infinity potential is 0. Well, so I would like to make some more general things. So I would like to define the self energy as the energy required to assemble a differential charge dq, bringing from infinity to assemble a say charged ball. Okay, So you can also see as intrinsic energy. Intrinsic energy. So I would like to make a charged ball and a spherical cell, self energy. So this is a spherical cell having charge Q. You just find the self energy. Okay, and it is radius is r naught. How can you assemble this charge? You just bring a small differential charge dq from infinity and put it here and take q amount of charges. Okay. You bring a small dq charge slowly from infinity and put it here, and again a small dq charge. Repeat it again and again until you have collected q amount of charge on this surface. Okay, so you need to find your burden, and this burden will be stored at your intrinsic energy. So why when you put a small charge dq here, it will develop a potential dV. Okay. Small charge dq, then it develop a potential q by 4 pi epsilon naught r naught. Then you have a potential here is 0. Then what is the potential difference? Now if you want to put a charge, a small charge again dq at this on this surface, you have to do some work against this potential. This potential doesn't make you a lot to put so easily. You have to do some work. So a small dV, okay, but slowly, okay, remember, slowly, charge should be brought slowly, otherwise, some complexity may occur, it may accelerate, may radiate energy, so I don't want to go there because of this will be some electromagnetic radiations, and this, I will discuss all these things, this motion, charge, acceleration and oscillation, in different sections of the chapter, forthcoming chapter in the electromagnetic radiation. But okay, jump to the point now. What will the bug done? So you have potential Q. So Q V into dq. Okay, very simple. Now Q by 4 pi epsilon naught r naught dq. How much charge from 0 to q? Now this is your work done, and now this is your potential energy. Now you have q square 4 pi epsilon naught r naught into half. This is your self energy of the charged sphere. This is your self energy of a spherical cell. Spherical cell. Now, from cell, I also find the intrinsic energy of a sphere, charged sphere, uniformly charged sphere. Well, now I am you should be very comfortable with all this argument. This is very so simple. Okay, so the question arises when this energy, I tell you one thing, this energy depends upon the R. Suppose we have same amount of energy and you expand the radius. This means you are changing the energy. Then you have to do work. Work done will be change your potential energy. When just expand or shrink this sphere, you need to do some work done. Okay. Because energy depends upon the radius. Whenever you reduce or increase this radius, you have this potential will change, and work done is changing potential energy. Okay. This is not interaction energy with the field. This is only the self energy. Assembling, certain amount of work done you have to do to assemble this. Okay, I can give this name assemble energy. So this is your expression. Okay, so I think we should be comfortable of all these things. This is very basic, a little some bit of integration. It can be evaluated. Now let me find the intrinsic energy for a charged solid, a sphere. Now this time self energy of charged a sphere and uniformly charged sphere. This is, I'm interested in finding this one. Well, how will you make a sphere? From a small, this small collection of the charges, make it big, make it radius higher, putting more amount of charges, again make radius more, putting a little bit more charge, again do this, okay, again do this, again repeat once more. So in this way you can have assemble this sphere. So it can have a total charge Q. Q is the total charge I have assembled. In the same way, bringing from infinity a small dq charges from infinity. So Q is the total charge, and R is the radius of a sphere. R is radius of a sphere. So we want to find electric potential energy of this assembles, this given charge distribution. Well, let at any time. Okay, we have this for study purpose, that is make it large. This is your radius R, and at any time, okay, this radius will progress and becomes equal to R, adding some more charge, putting it over this volume. Okay, this is your volume, so putting charge on this volume, this will become large and finally reach to this radius R. So at any time t, suppose at any time t you have a charge Q. So already I have brought charge Q, then brought QQ charge. You have to this configuration must have potential. Okay, so you need to do what? dq. Just integrate. Now you will get the energy. Now, what is the potential at this surface? This is the surface. So, you know, potential is nothing but Q by 4 pi epsilon naught R. But what is the amount of charge Q? How will write this charge Q? Q have to write density. It should be given as density, charge per volume, into 4 by 3 pi R cube. And what will the density Q by 4 by 3 pi R cube? This R cube into 4 by 3 pi R cube. This is your charge per volume, and this a small amount of volume, this contains charge Q. Okay, so now dq, add a small dq over the volume. Now volume, that is 4 pi r square dr. Okay, just make this volume again dr. You can add this dimension dr to make radius r from r to sorry, R to R plus dr. The small, this is the dV small volume, this is your small volume. So be comfortable with all this expression. Now I have dq. So we have 1 by 4 epsilon naught r q. You can write this density into 4 by 3 pi r cube, again dq, again density 4 pi r square dr. Now integrate with 0 to 2r. Okay, and I can get a potential energy. So r 1r 4 pi will cancel, another 4 pi left with. So we have 4 pi density whole square r 4 dr 3 epsilon naught. Okay, now integrate it with 0 to r. No, I have experience of solving this. I know the answer because otherwise, for a spherical cell, now it is a 0.6 into q square by 4 pi epsilon naught by r. I have remember like this, q square 4 pi epsilon naught r for solid sphere, and for cylindrical cell, a spherical cell, it had 0.5 into q square by 4 pi epsilon naught r. I mean to say q square by 8 pi epsilon naught r. This is for a spherical cell, and you just write 6 by 10. You can write 3q square by 20 pi epsilon naught r. You may, you may not remember this expression always, but once you can understand q square of 4 pi epsilon by r, just multiply 0.5, you can get it potential energy for a cell, and again multiply with 0.6. With this quantity, you can get potential energy for a spherical, this sphere. Okay, so this is your potential energy. Now do some problem. Okay, easy problems. What is you can get it in irodov. You can see this question in irodov also, of radius r1 with charge q is expanded to a radius r2. Find the work performed by the electric forces in this process. Find the work performed by the electric force in this process. This is your question. Okay, self energy. Again, I can write this. This is the same 0.5 into q square by 4 pi epsilon naught r1. Now radius is going to be r2, then you find u2 is 0.5 into q square 4 pi epsilon naught by r2. Now work done, negative of change of potential energy. We have q square 4 pi epsilon naught into 0.5 1 by R1 minus 1 by R2. This is your work done. And of course, in conservative field, hold on to this one. Okay. This is so enlightening, you know. This is so good thing, I think. It's very only, you know, physics is a small thing you understand, and everything will be easy. Okay. No further explanation. If you understand one thing, you can express different things. In all combine to each other, all come to converge to a different same point. So this is your answer. Now another one. Suppose we have a cell. Now question, a spherical cell of radius R1 with a uniform charge Q has point charge Q naught at center here, Q naught at a center. At center it has point charge Q naught, and it is a cell having radius R1, and this Q is amount of charge over the surface. Now find the work performed by the electric force during the cell expansion from radius R1 to R2. Okay, okay. Now expand, same problems, but we have one more charge Q naught is placed here. Again, same thing, self energy, change in the interaction energy. You have, you know, this charge will interact with this charge. So you have here, if you write the energy, then you have to write self energy. It will depends upon R, and also the interaction energy between the two charges. It also depends upon this distance R1, interaction energy, and both will change when radius will be changed, because this self energy depends upon the radius, and interaction, you know, also depends upon the radius, distance between the two charges. Of course, both are going to be altered, and change in this energy, you know, overall energy is required work done. So initially you can write self energy 0.5 into Q square 4 pi epsilon naught R1 plus interaction energy Q by Q naught 4 pi epsilon naught R1. Now you final 0.5 Q square 4 pi epsilon naught R2 plus Q naught 4 pi epsilon naught R2. This is your energy, final energy. So you know, work done, negative of change of energy. So you can subtract this. You can find this. So I think that thank you. Now next classes I will discuss new things about this electrostat. Thank you.